So hello and welcome students. So today let's start our discussion. This is lecture number MA412 linear algebra, and lecture number 11. Okay. Now recall in our last lecture we discussed about dual spaces, space of linear functionals, right? So the natural question. I mean, there are many questions. One such question is that are there any relation between these linear functionals and the subspace of the space? So we have a vector space, and then we have a dual, then we have double dual, right? And then we showed that they are all isomorphic. In fact, V and V star are something called canonically isomorphic. This is canonical isomorphism. Canonical isomorphic. So what does that mean? That means that for every element of V, you can define the element V star canonically, which actually is a linear functional on V star. Okay. So one such question one can ask that are there any relation between question, or rather I should say is there. So is there any relation between what is that linear functionals, linear function, between a linear functional and a subspace of V. Okay, subspace of V. Okay. So I have a vector finite dimensional, so I am assuming finite dimensional. So maybe I can talk about something about infinite dimensional maybe at the end. Okay. So for the time being, I am assuming the dimension of my V is finite, and I know that then V is actually isomorphic to V star and V double star also. So are there any relation between these kind of functionals and subspaces? For example, so if you start with a linear functional, so if you have f belongs to V star, so that means linear functional on V, then there are two options, right? Then either so what type of options are there? There are two options in the sense I mean to say that the rank of that f. What are the options of that? Then either rank of f is 0 or 1, right? There is no other option because the range of f is f is dimension 1 subspace of f, right? There are two options, either rank will be 0 or f. So 0 means what? So 0 means that all this functional sending every element of V to 0, right? So this is a 0 functional. This is actually 0 functional that I already discussed. 0 functional. And this is actually coming, 1 is coming for any non-zero functional. Non-zero function means that it cannot send every non-zero element to 0. There must be some non-zero element whose image is non-zero also. Okay, non-zero functional. There are two options, right? 0 or non-zero. Now, in the case when rank of f is so when this rank of f is 1, then you can use rank nullity theorem to get something, right? Then by this rank nullity theorem, what does the rank nullity theorem tells us? This rank is 1, right? So rank of f plus nullity of f equal to dimension of v, right? Which is finite dimension, I already assumed. So this is 1. So nullity means this nullity. This implies that nullity of f equal to that dimension of v minus 1. So let me assume that this is n. So I'm assuming that dimension of v equal to n. This is n minus 1, right? So what does that mean? That means if you have a linear non-linear functional, then the nullity of that functional must be n minus 1. What does that mean? So the null space has dimension. So that means the dimension of the null space, dimension of the null space n of f, which is the null space of f, is actually n minus 1, right? So the null space is subspace of the vector space, right? Which is dimension n minus 1. That means this is just one dimension less than that. Okay. So this type of subspace are called co-dimension. See, one dimension 1 less means the co-dimension is 1. Co-dimension means co-dimension of a subspace means this is total dimension minus the dimension of the its subspace. Okay. So this type of subspace are called actually hyperspace. Okay. So how do I define hyperspace? So so let me define here. So for find the hyperspace, I'm defining first. So let let v be a finite dimensional yeah, so somewhere I wrote here finite dimensional vector space over if is a field. Okay, then any subspace of dimension this dimension equal to equal to the dimension of v minus 1. Okay, so if this is equal to this is called a hyperspace. Okay. So what do you mean by hyperspace? Hyperspace are the that is high space. Hyperspace are the co-dimension for finite dimensional vector space. This is the definition. Okay, for infinite dimensional vector space we can define by different method. Okay, maybe I will tell you later. Okay, so hyperspaces are the subspaces of co-dimensional one So what does that mean? Coulomb sum means that it is actually dimension 1 less than the original space. Okay, that's called hyperspace. Now, as per our discussion from before, it is clear that if you start with a non-zero functional, the null space of that is that hyperspace, right? So example. So null space means kernel. Okay, null space, or we can say kernel also. Of any non-zero or non-trivial or whatever. Okay, non-zero linear functional is a hyperspace. That is obvious, right? Because whenever you have a non-zero functional, that rank has to be 1, and hence that null spaces dimension is n minus 1, right? That is the thing. Now the question is that what about the converse? So one can ask question, does the converse holds true? So that is what I am asking. I'm asking whether every hyperspace. So we just proved that null space of linear functional, non-linear functional hyperspace, right? So now asking converse whether every hyperspace is a null space of some non-zero linear functional or not linear functional or not. Okay, I don't know, I'm just asking. Okay, and the answer to this question is actually yes. So the answer is yes. Every non-zero linear functional is actually null space of every hyper subspace is actually null space of some non-zero linear functional. Okay, in fact something more is true. If we start with the subspace of dimension say k, and then you will have actually and the dimension of the full space is n, then you have actually n minus k many linear functionals whose null space intersection null space actually contain this subspace. Okay, so the answer is yes. So answer is yes. Okay. In fact, mode is true. So what is mode? So what I can say? In fact, indeed, or in fact, we should say in fact, not indeed. In fact, more is true. What does that mean? So that is, I am saying that you can say something more, that each or every k-dimensional subspace of a n-dimensional vector space n-dimensional vector space is the intersection of the null space of n minus k many linear functional. Okay, I will prove this, don't worry. So in fact, when k equal to n minus 1, then you will have the answer. When k equal to n minus 1, then this subspace is a hyperspace, and n minus n minus 1 equal to 1, right? So then there will be exactly this is null space of single linear functional. Okay, so this part is okay to everyone. Now to understand this, we need a new idea. What is the idea? So let us define something called annihilator. Okay, so definition. So let be vector space, any vector space. Okay. I'm not assuming that V is finite dimensional, not vector space over some field F, and you choose a subset of A is a subset of V. Okay, so S may be any subset, it need not be subspace. Okay, so then we define the annihilator of annihilator so annihilator of S is the set is not, which is defined by, which is defined as, what is not is collection of all linear functional on V, that may element of V star, such that F actually sends every element of f of V equal to V0 for all V belongs to S. So inside S, so S is subset of V, right? So there are some vectors of S. So it sends all the vectors of S to S, right? So if this is the case, then we say that this set, this collection of all such linear functional, he sends this, is called the annihilator of S. Okay. So obviously you can say that this is always non-empty. I mean, it has to be, so zero function is always there. Okay, so that you know that. Okay. So okay, and not only that, you can also say that it's not, it's actually not only a subset, it's also a subspace actually. Okay, whatever the S be. So note that is not is always a subspace of V star, whether no matter what is whatever, no matter whether S is subspace or not, right? So whether S is a subspace or not. Okay, so S is subspace or not doesn't matter. Okay, subspace or not. Okay, so how do you prove that H is subspace? So what does that mean? Subspace means this is itself a vector space, right? And so you have obviously that zero functional, so that is from V to F by V is that sense every element to 0 for all V belongs to V, right? This is zero functional. This is the element of V star. So the zero functional is always belongs to S naught, right? Because for any S doesn't matter. Zero functional sends every element of S to 0. So zero functional is always belongs to S naught, right? And now what you need to prove this subspace. So you already know that this is so closed under addition and multiplication, that in scalar multiplication that you need to prove. Now closed under addition means what? So if you start with two functional, next point. So this says that this sign out is always non-empty. Sorry, it's not non-empty. Okay, and then if we choose two elements f1 and f2 belongs to S naught, okay, then obviously you know that f1 of V equal to f2 of V equal to 0, and that is true for all V belongs to S now, S, right? V belongs to S is capital S. Okay, so thus if you add these two things, so f1 plus f2, that of V will be f1V plus f2V, which is 0. Okay, and you can multiply by similarly you can multiply by the constant of V, that is also C times f of V. Okay, that is 0, right? Because f is, or you can choose f1, doesn't matter. For this is true for all, this both are true for all B belongs to S. So what does that mean? That means it's not, it's a subspace, right? So that shows that S1 is a subspace of V star. Okay, S may not be subspace also, right? So this is first property, property number 1. So, and property number 2 is what? So you see that if W is a subspace spanned by S, S may not be subspace, but you can take the smallest subspace spanned by S, right? So you take a linear combination of all elements for S, that will form a subspace, right? If W is subspace of the X, if this, then you see that this W, this annihilator of W is actually same as annihilator of S. Okay. Now how do you prove this? So one part is obvious because AS is okay. So AS is as S is sitting inside W, right? So what is the relation between annihilator? Then annihilator of S is actually the other way direction, superset of W, annihilator W, right? Why? Because if if you choose the annihilator of W, that is functional, which actually takes the same every element of W 0, so that also same the element of S 0, so that belongs to the set. So this one is obvious, that if it belongs to annihilator of W, that this implies f of W belongs equal to 0 for all small w belongs to capital W. Okay, this implies f of V belongs to 0 for all V belongs to S, because S is also W, and this implies f belongs to S now, right? So one part is obvious. Now we need to put the converse also. Converse means what? That so the annihilator of S is also subset of W. That we need to prove, right? Now claim. So this is our claim that annihilator of S is also inside this, right? So what does that mean? That means if you start with one element of S naught, and so let, how do you prove this? So let f belongs to S naught. So S naught means that this implies f of V equal to 0 for all V belongs to S, right? Now so if since every element of S is 0, that it also sends every element of W to 0. Why? Because W is a space spanned by S. So what does that mean? That means now for any element, so now for any element of so W belongs to W, we know that, what do you know? You know that small w is a finite linear combination of element of S, right? That is by definition, because W is the space spanned by S. So every element W is a linear combination of element of S. But if sends every element of S to 0, and hence, so thus if is linear also, right? So thus f of W equal to 0 for all W belongs to capital W. What does that mean? That means f is element of annihilator of W. Okay, so thus this is not is subset of W naught, and finally we have they are same. So if you start with a set which is not a subspace, the annihilator of the set is equal to the annihilator of the subspace formed by the set. Okay, so this is the proof. Now with the help of this idea of annihilator, we are going to prove our question. Remember what we asked, that converse holds or not. That means if you start with the hyperspace, whether it is actually null space of some non-zero linear transforms or not, we are going to prove actually more, and the special case will be that. Okay. So now what we are going to prove? So our theorem is that so this is the theorem. So let so I am assuming finite dimensional, obviously. So let V. So let V be a vector space over F with say dimension of v equal to n. Okay, and we have a subspace W, which is subspace of V. So this is the symbol of subspace. You recall that. So in this case, then what happened? Then you can say that dimension of W is actually dimension W plus the dimension of the annihilator of W. Annihilator of W is actually equal to the dimension of V. Now, this is kind of similar. You understood that this kind of similar things with the rank-Nadi theorem. Indeed, this is actually similar because you just showed that this is kind of some kind of a null space, or it's a null space, right? That you will show. Okay. And then done. So then how to prove this theorem? The proof is similar to that rank-Nadi theorem. So you start with a subspace. So let something say beta 1. So this is something. So I'm assuming that dimension of W equal to say k. Okay. So vk be a basis of W over F. So W is a subspace of dimension k. Okay. Then extend this basis. Extend B1 to a basis of V. Say, let me write down, it's a V. And what is V? So V contains that first V1, V2, Vk many elements, and then Vk plus 1 to Vn elements till Vn, right? So this is a basis for V. And once you have a basis for V, then you also have a dual basis for V star, because W naught is actually subspace of V star, right? And let so V star, let me write down here something, say F1, F2, right? Fn be the dual basis of V star. Okay, that is here if I Vj equal to this Kronecker delta Ij, right? I mean, you remember this is 0 if I not equal to j, is 1 if I equal to j. Okay, Kronecker delta. So this is so I choose a dual basis, and now I'm claiming that so after that kth position, so now what is our claim? So our claim is that so f1, f2, fk is okay, but then after k, if you choose fk plus 1 to up dot f of n, so this is a basis for W naught, the annihilator of W. This is our claim. And then if you can prove that, then we are done, because the dimension of W naught will be n minus k, and dimension of W will be k, so the sum will be n exactly, right? So this is similar to the proof of Rank-Nadi theorem. Now obviously you need to first check that whether these vectors or the linear function are the element of V star, W star or not. So note that before proving, just note that for example f of k plus 1. So this is true for any if k plus 1, if k plus 2, fn. So I'm just showing you for if k plus 1. F of k plus 1 of vi equal to always 0, right? For all I equal to 1 to up to k, because this dual basis, right? When I equal k plus 1, it is 1, otherwise 0. So what does that mean? That means f of k plus 1 is an element of w star, right? Because bi forms the basis of w. Similarly, all those like and so on. F of k plus 2, if they all are element of w naught, because they vanishes on the basis of w. Okay. So these vectors are element of w naught. That is not a problem, right? And also this is linearly independent. That you already proved last day, that these coordinate functionals from coming from coordinates, they are actually linearly independent, right? So the only thing is that also they are linearly independent. That let me write down also. So let me write down the name. Let b dash. Also b dash is linearly independent. So thus we need to prove only. So thus we need to prove that b dash is a spanning set of w naught, right? Then we are done. Prove that this span of b dash is actually w naught. Then we are done. So what does that mean? That means every vectors inside w naught. So that means every linear function of w naught, they actually coming from this only k many this n minus k many vector, right? Now how do you prove this? So now you start with so remember the definition of linear functional. So for any now recall that for any linear functional on V star, how we can write down that f can be written as summation of f of vi f of I equal to 1 to n, because if I is a dual basis of the basis vi, right? And but you know that if we so this is in general. Now if this now if it belongs to w naught, then what happened? I need to show that every element of w naught is an element of it's spanned by element of b dash, right? Now if this belongs to w naught, then what happened? Then we know that if of vi is at 0, then f of vi is at 0 for all I equal to 1 to up to k, right? Because this till vi vk, this forms the basis of w, right? So what does that mean? That means then you can write down f equal to f of vi and fi, and here I from k plus 1 to n, because before k plus 1 f of vi are 0 by definition of w star w naught. Okay. And hence, so what does that mean? That means if f is element of w naught, then it is actually in a combination of this. So that means that w naught is actually span of b dash. This is the proof actually. So what does that mean? That means this is actually so what does that? So that means that dimension of w naught equal to exactly n minus k. And we also have dimension of w equal to k, right? Dimension of w equal to k, we already start with that. So thus dimension of w plus dimension of w naught equal to and the dimension of V, right? And our original question was what? Our original question was whether we can do it like there exists for given any linear, given any hyperspace, there exists a linear functional or not whose null space is the hyperspace, and the answer is yes from this, because now you choose if you choose W as dimension k in minus 1, then W will be dimension 1, right? So that means there will be exactly one linear independent linear function, right, whose null space is this W. Okay, so this is obvious. So the proof is obvious. You can so as a corollary, what you can say, what we ask also corollary, that if W is a k-dimensional subspace, of V, so V with dimension of V equal to n, so I'm just, let me write down again here, then what you can say, so then W is the intersection of this n minus k many hyperspaces in V. Okay, and the proof is simple from the theorem, because for each of those, so for each if of I equal to say k plus 1 to the way I prove it. So for each of those things, what happens? So f of I of small w equal to 0, right, for all w belongs to w, right, the way we prove it. So this the annihilates the element of w. So what does that mean? That means for each of so for each of this fi, the null space is dimension n minus 1, right? Because if you have non-zero linear functional, then the null space will be dimension n minus 1, which is hyperspace, right? So you can write down that. So let hyperspace. Let me write down that. What should I say? So maybe each I is the null space of fi equal to k plus 1 to n. So they are null space. So all those h actually contains w, right? W. Then this is obvious. So w is actually sitting inside all those hi's. All I equal to 1, k plus 1 to n. Why this is true? Because if something belongs to w, and so this is null space of fi, right? Okay, so what I said, otherwise this intersection actually, I must say that. Okay. Yes, so this is actually intersection of that. You can prove both sides. So from that you can say that this is actually subset of intersection of each I, because it is inside all the each I, and converse is also true, because if it is intersection of these, then it is actually belongs to null space of each I for all I, and hence other than wi, everything vanishes, right? So it's actually null space of wi. So this both sides are same. So w is actually intersection of this null space of those FIs. And how many such FIs are there? I equal to k plus 1 to n. How many such are there? N minus k many exactly. K plus 1 to n, there are n minus k many elements, right? So that tells you that given any subspace of a vector space dimension k of dimension whole space dimension n, then is actually intersection of some hyperspaces, nothing else. So always hyperspace intersect with subspace. Subspace are actually, you can think of the hyperspace and their intersection. Okay. So in fact, you can also say some characterization of the subspaces in terms of annihilator. And so next observation or next corollary, you can say that, or next proposition, whatever you say, that if you have two such subspace W1 and W2 are subspaces of this fine dimensional vector space, say V is fine dimensional, okay, of V with this, then you have some characterization. What is that? Then W1 equal to W2 if and only if condition, and their null space are same. So the null space of W1 equal to null space of W2. Okay. So again, one part is obvious here. So proof. So one way obvious, right? So if this one is obvious, if W1 equal to W2, that will always implies W1 not annihilator W1 equal to annihilator of W2, right? Because if they are equal, that means those vectors, those linear functionals which annihilates every element W1 is also annihilated by W2, and they are same, right? The converse part is the interesting part. Conversely, if W1 not equal to W2, okay. So suppose it is not equal to W, then we will show that W1 not is not equal to W2 not. Or rather, you can prove the other way also, W1 not equal to W2, then they are same. But okay, so this is also okay. So if W1 not equal to W2, then we will show W1 not is not equal to W1, W2 not. So if W1 not equal to W2, then what happens? Then either so one has to be so there will be vectors V which is belongs to one set is not the other set, right? So you can say that W1 something like that. I mean, obviously this is one such example I am telling you. But if they are not equal, so there might be some vector V which is sitting inside. So there will be some V belongs to V such that V will be either in W1 or W2 but not in the other one. So I am assuming V is W2 such that V is inside W2 but or other W2 minus W1 is okay. So it's inside W2 but not inside W1. You can choose W1 on other way also. You can choose V belongs to W1 not belongs to W1, W2. The same. So there is no. So this is without loss of. So this is, we should say that without loss of any generality, means that if we choose this element of W1 or W2, then also same group goes. Okay. So they are not equal, so you will have the vector V that is inside one subspace, not inside the other subspace, right? Then what happens? Then you choose again you choose a basis of W1, okay, and then extend it to basis of W2 with this, okay. So then choose say v1 some basis v1 v2 vk basis of w1, okay, and then extend it to basis of v containing that v is not inside w1, right? So that means v is linearly independent with the v1 with vk. You can add always, that will be again linearly independent, right? So what does that mean? That is, so you can write down mu v, which is v1 up to vk, and then v, and then vk plus 2 to vn. Okay, so what is the advantage here? Because v is not inside w1, outside that, so this is outside span of v1 v2 vk. So these are linearly independent. V is linearly independent with v1 v2 vk. So this is a basis of v, right? And then what will the dual basis? So dual basis will be how? It will look like f1 f2 fk, then something say fk plus 1, which I am writing f only. Let me write down by that fk plus 1, fk plus 1, I am writing f, and then rest is fn, whatever the same, right? Now what happened in this case? You know that this f1 f2 fk, they all so this after fk plus 1 they all annihilate this, right? So fk plus, in fact, so then this f of vi is equal to 0 for all I equal to 1 to k, that is f of w equal to 0, w equal to 0 for all w belongs to w1, right? Because this is element of w1, v1 v2 vk element of w1, right? But what happened f of v? F of v is not equal to 0, f of v equal to 1 by definition, right? But f of v not equal to 0 is actually 1, right? So let me write down that v equal to 1, which is not equal to 0, right? So thus f is an element of, so f annihilates every element of w1, right? So f is inside w1, not, but f does not belongs to w2, not because there is an element v inside w2, which does not annihilate that element, right? So what does that mean? That means w1 not cannot be equal to w2 not, and hence the proof. So this completes the proof. This completes the proof. Now question is that how to define it for infinite vector space. So for infinite vector space, what you can do, you can define it by the maximal proper subspace of V. See, so concept of maximal, I already told you, maximal means that, so this is a proper subspace, but it is not inside any other subspace. What does that mean? If it is inside any subspace, that has to be equal to itself, right? So in that case, so let me just define it. For the case of infinite dimensional vector space, we define hyperspace by hyperspace by a maximal proper subspace. Okay, geometry proper, maximum proper subspace of B. Okay, and now you also maybe I'm giving homework that in this case also you can prove that um, every hypersurface is actually is actually null space of some linear functional. Okay, and vice versa. So if you start with this some linear functional of infinite vector space, then the null space is also hyperspace. That is obvious, and the converse is also true. So you can think as this problem is homework. You can do it. Okay, maybe I will stop here for today's lecture. Okay.